Hello everybody, welcome to Mrs. Baker's Chemistry Corner. This is Module 5 Monster Paper Walkthrough for the Paper 4 version, and it's question 6. So let's get stuck in. This question is about masses, volumes and moles. So which term is defined by the following statement? The average mass of a naturally occurring atoms of an element on a scale where carbon-12 atom has a mass of exactly 12 units. Well, of course, that is talking about the relative atomic mass scale, because relative atomic mass tells us that every atom is compared to carbon-12, and carbon-12 weighs exactly 12 units. So butane has a relative molecular mass of 58, but potassium fluoride has a relative formula mass of 58. We'll explain why the term relative molecular mass can be used for butane, but cannot be used for potassium fluoride. So it's 2 marks, and it said you have to explain why it cannot be used for the other one. So you must say both quantifying situations for the mark. So you must talk about both butane and potassium fluoride. So C4H10 is covalent, so it's a simple molecule, but KF is ionic. So it's a formula because it's a giant ionic lattice, hence a formula mass and a molecular mass. Okay, a 0.95 gram sample of gaseous element Y, let's highlight, occupies 60 centimeter cubed at RTP. Determine the number of moles of element Y. Well, we don't need to jump into a table method just yet because it's only talking about element Y. There is no molar ratios to worry about. We're just talking about magic triangles here. So it's given us the mass in grams, and it's given us the volume that it takes up as a gas. It says it's a gaseous element. Don't miss that fact. So if it's given us the volume of the gas, we can divide that by 24, which will give us our moles. So let's plug it in. 60 needs to be divided by 1000 to get it into decimeters cubed. So let's do that first. 60 divided by 1000 gives us 0.06. So that's our volume in decimeters cubed. We can divide that by 24 because that's what our magic triangle tells us to do. And so that's 0.0025. So 0.0025 moles of element Y. It then asks us to calculate the relative molecular mass of element Y and then suggest the identity of element Y. Well, if we need to now calculate the relative molecular mass, we've got the moles and it's given us the mass up here. So all we do is we do mass divided by the number of moles. So we've got 0.095 and we must divide that by 0.0025. What does that give us? Let's see. That gives us a molecular mass of 38. So we now need to identify the element Y. Well, we use what the information in the table has given us. It says it's a gaseous element. So at room temperature and pressure, it's a gas. So we think it's probably going to be a non-metal. There are no metals that are gases at room temperature. So we're going to be looking on the right-hand side of our periodic table. If we look on the right-hand side of our periodic table, well, most of the things on the periodic table that appear as gases are diatomically bonded. So we know there's going to be 2 of them. Let's have a look. If we go over to oxygen and nitrogen, all those things that are kind of gases at room temperature, remember it's an element, so it has to appear on the periodic table. You can't be looking for carbon dioxide or something like that. It's already told you it's an element. So let's have a look. Well, oxygen and nitrogen, they're going to be two less. They're going to be less because, 16 and 16 is 32. So go one next door, 19. Well, 19 times 2 gives you 38. So I reckon it's fluorine. So identity of element X is fluorine. How do we know it's 2? Because we have no fear of ice cold beer, and we know that most of the gases, the elemental gases there, are diatomically bonded. A 1.68 gram sample of phosphorus was burned and formed a 3.86 grams of an oxide of phosphorus. Calculate the empirical formula. Okay, so it's told us that we had 1.68 grams of phosphorus, and then we had 3.87 grams when it bonded with the oxygen. So we need to find out how much oxygen we had. So we need to do 3.87 minus 1.68. And so that gives us 3.87, and we need to minus 1.68. That will give us how much oxygen we used. Turns out we used 2.19 grams of oxygen. So we've got phosphorus and we've got oxygen. We had 1.68 grams of phosphorus, and we've got 2.19 grams of oxygen. Now we just follow our step-by-step formula for finding the empirical formula. So we'll say this divided by 16. We'll say this divided by phosphorus. The mass of phosphorus is 31. That will give us our number of moles. Let's do that. 1.68 divided by 31 gives us 0.0541. 0.05419. And we will do 2.19 divide by 16. That gives us 0.136.875. Remember, in empirical formula, try and keep as long a calculator value as you possibly can. So in this case, our smallest number of moles is the 0.051. It's the phosphorus. So we're going to divide everything by the phosphorus, 0.05419, and we're going to divide this by 0.05419. So that will give us 1. So we're going to do 0.136875, and we are going to divide that by 0.05419. And that's going to give us 2.5. Well, we can't have 0.5 of a atom, so we're going to need to times it up. 2.5 times 2 equals 5. So whatever we do on this side, we also have to do on this side. So 1 times 2 equals 2. Therefore, our ratio is 2 to 5. So it's going to be P2 and then O5. Remember, if you times it by 2, you didn't get a whole number, you'd have to go to times 3. And if you didn't get a whole number then, you have to go times 4. And if you didn't get a whole number then, you get times 5. But luckily, 2.5 times 2 is 5. It's a nice round whole number. Another oxide of phosphorus has the empirical formula P2O3. One molecule of this oxide of phosphorus contains 4 atoms of phosphorus. Calculate the mass of 1 mole of this oxide of phosphorus. Well, if the phosphorus contains 4 atoms, the empirical formula is just a ratio, remember. So if the molecule itself contains 4, then we've got P4. Well, we've times P2 by 2, so now we need to times O3 by 2, because remember, we must keep the ratio the same. So that would be O6. What's the mass of 1 mole? Well, we know that the mass of 1 mole of anything is just its relative molecular mass. So phosphorus, we've already established, is 31. So we're going to do 31 times 4 plus 16 times 6. What's that on our calculator? 31 times 4 plus 16 times 6, 220. So the mass of 1 mole of that oxide would be 220 grams.